Right, so here we're coming back to the ideas of inverse functions, which were introduced in a lesson a while ago, and looking at the idea of a composite function, which essentially means a function inside a function. And this notation here, this sort of floating little circle thing, represents this. And so we could say f of g of x here, which means g of x is inside function f. And the order that you compose a function very often matters. And so if we look at something like this, don't assume that g inside f is equivalent to f inside g. Don't assume that. And so here I have two functions. Function f is a quadratic function. Function g is a radical function. And I want to look at the two different compositions as well as the domain and range of each. So let's first start with f of g of x, which I can write in a few different ways. But most importantly, what it means is we have function g of x inside function f. And in this case, function g is just root x. So we have root x going into function f. And function f is x squared minus 1. So we want to be clear on what this means. If I put function g inside f, then the idea is that root x replaces the input, replaces the x. So instead of x squared, it's root x squared. Take away 1. We got to be a little bit careful here. Root x squared, take away 1. And this is where we got to be careful, because root x squared, it's easy to simplify it down to just x, which is not completely wrong, but it is wrong to say that this is the simplified answer, because this implies that f of g of x is exactly equivalent to this linear function x minus 1. But if we I want to graph this function, and I really want to graph this right here, root x squared, take away 1, because that is essentially what this function is. I've just simplified it down to x minus 1. And there's one little mistake if I just simplify it like this and move on, and which we can tell if I look at the graph. So right here, I can see the graph. I can see the graph of, turn that one off. I can see the graph of root x squared minus 1. And notice what we see is a linear function, but it starts at 0. It doesn't have a domain of all real numbers. And that's because the square root of a negative number is not real. And I'm graphing only real numbers here. And if I look at this graph, then I need to realize that it is equivalent to the graph of x minus 1, a linear function with a slope of 1 and a y-intercept of negative 1. But it begins only at 0. When x is negative, this function is undefined, essentially. And that's, if I look right here, I need to realize this equation of x minus 1 implies that x can be any real number. And so I need to put a little comma and say x must be greater than or equal to 0. And that all comes from the fact that that's the case for the inside function, root x. For us to evaluate root x with real numbers, we need x to be 0 or greater. And that's also therefore my domain. So if I want to state the domain of this function, well, I've already stated the domain. The domain is where x must be greater than or equal to 0. Again, if I didn't have that chunk there, then I'm implying the domain is all real numbers, which, as we can see, is false. The range, well, I can tell just by looking back at the graph here. If the domain is only values from 0 and up, that means my function has a lowest point right here of negative 1, but it has no maximum point. So the range is from negative 1 and up. And so I'll write that as the range is greater than or equal to negative 1. All right, so now let me compose these the other way around. Let's look at g of f of x, which means f of x is inside g of x. Well, f of x is x squared minus 1, and that is going inside function g. G of x just is the square root of the entire thing. So this then is the square root of x squared minus 1. So there's the equation. So now, what's the domain? Well, one thing I could do is if I just graph this right now, that perhaps may make it easier, and you may have noticed I actually accidentally graphed it a moment ago. So let me turn this off and turn this on. And notice the domain is not all real numbers. The domain is everything except from negative 1 to 1. And if I look at my graph here, I can see negative 1 and 1 are these sort of beginning and end points of this little hole in the middle, which, if we analyze the equation, should make complete sense. Because if we look at this part right here, the x squared minus 1 part, when x is between -1 and 1, x squared minus 1 gives out a negative value. And the square root of a negative value is not real. And so the domain is everything but the values between -1 and 1. A few ways of saying that. I'll say it as x must be less than or equal to -1, or x must be greater than or equal to +1. Or I could write using different notation. I could say round bracket, -infinity to -1, and then the union of that with 1 to +infinity. That's it. That's my domain. My range, or all the outputs, again, just going back to the graph. I can see it's everything greater than 0, including 0, and if I zoom out, it actually behaves like an absolute value function after a while. But it's everything greater than 0 or equal to 0. Keep in mind, quite often when determining domain and range, the graph of a function really helps, and we always have access to graphing technology in this course. All right, so next I want to go back to inverses, and I look at a cubic function, f of x being x cubed minus 2, and I want to find the algebraically, I want to find the inverse, which we talked about in a previous lesson. And then I want to show that this inverse is correct by looking at this, which is if for any function, if we correctly found the inverse, then if you put the inverse inside the function, or if you put the function inside its inverse, you should always end up with the same thing, which is just x. It essentially means you put in x and you get out x, which means the two functions are undoing each other, which makes sense. They are the inverse of one another. So let's first look at putting the inverse inside its function. Well, I guess actually, first things first, let's find the inverse. And so I'm going to rewrite f of x as y equals x cubed minus 2. And we've talked before about how to find the inverse. One of the most standard ways is you swap your input and output. So you swap your x and y, and you get x equals y cubed minus 2, and solve for y. Add 2 to both sides, cube root both sides, and you get y equals the cube root of x plus 2. Keep in mind with a cube root, there's only one possible value. Negatives make sense going into a cube root. There's no need for a plus or minus here, and therefore my inverse in terms of x is the cube root of x plus 2. All right. There's my inverse. In yellow, there's my original function. So first, let me look at this here, where I have the inverse inside f. And so the inverse is the cube root of x plus 2. And I want to put that inside function f. And function f is x cubed minus 2. So it's the whole input. It's all of this cubed. So it's the cube root of x plus 2. But all of that cubed, and then having 2 subtracted from it. Well, the cube root of x plus 2 all cubed, put that little bracket back there. Well, the cube root and a power of 3 are inverses of one another, so they cancel out. We just have x plus 2, and then that minus 2 plus 2 minus 2 is 0, clearly, and so I do indeed get to just x. That said, to prove that this really is the complete inverse, it should work the other way around. So let me also take f of x, which is x cubed minus 2, and put that inside the inverse. I should also get to f. And so the inverse, as I found down in there in blue, is the cube root of x, which is the input. In this case, my input is x cubed minus 2 plus 2. And again, what I'm essentially doing, if you're unsure about any of that, is what you see highlighted in yellow. That is what I substituted right there. So instead of substituting x into here, I'm substituting x cubed minus 2. That's it. That highlighting is getting a little bit messy, so let me focus back on this. And I can see I got my minus 2 plus 2. Those make 0. And then I have just a cube root of x cubed, which is just x. And lo and behold, yeah, I got just x both times. And so I've just confirmed in a different way that my inverse is correct. All right, lastly, let's look at a new function, function h, which is a radical function or a square root function. It's just x, the square root of x plus 2. I want to find the inverse, but then I want to graph both on here. And we got to be, this question can be deceivingly tricky. So let me get straight to it. Let's find the inverse. So I'm going to write h of x as y equals root x plus 2. I'm going to swap around my input and output, and I get x equals root y plus 2. So to isolate y, I want to square both sides. X squared equals y plus 2. Subtract 2 from both sides, I get x. Actually, I'll write it like this. I get y equals x squared minus 2. Or I can say the inverse of h is x squared minus 2, which is partially wrong. So I got to be careful. It's not completely wrong, but there's something incorrect about this, which I can get a sense if I look at the graphs of these things. So let's graph these. So first, root x plus 2. I want to sketch the graph onto here, which I can just quickly show you in Desmos here. So here's root x plus 2. If we're familiar with what root x looks like, it is the graph of root x just translated 2 to the left. Pretty easy to draw. I'll use the points negative 2, 0, and a few other nice points to kind of sketch this. But there's root x plus 2. So goes through here, also goes through 2, 2. And again, for a quick sketch, this is more than good enough. All right, and let me label this. And this is, again, the function that we were given, h of x. So the inverse, I said there's something wrong with it. And we can tell there's something wrong with it when we graph it and remember something we learned a while ago, which is visually, if you look at a function and its inverse, they should be reflections of one another. They should be reflections of one another on the line y equals x, which is not the easiest mirror line to visualize, nor draw, apparently. Let me try that again. That's a little bit better. But if I just draw x squared minus 2, which I don't really need a graphing program to visualize, it's a quadratic function, move 2 down, but I got it right here anyways. I can see those aren't reflections of one another. The graph of x squared minus 2 is not, it's way more than the graph of root x plus 2. But it's not meaningless. There's a logic here. So I am going to draw it. I'm going to draw what I have there in red, but eventually I need to erase part of it. So x squared minus 2 looks something like this, where we have a quadratic. Oh, got a little off there at the end. We have a quadratic function, so a parabola like this. Okay? But like I've said, if these were fully correct, the two should be reflections of one another. These aren't reflections of one another. So what's wrong here? Well, let's look back at my original function, h of x, the graph in blue. I can see just by looking at it, this function here, h of x, has a domain where x is greater than or equal to negative 2, and has a range where y is greater than or equal to 0. Now I need to remember how that relates to inverses. Inverses, your inputs and outputs are all swapped around, which means your domain and range are swapped around, which means the domain of h of x is greater than or equal to negative 2, should be the range of my inverse. Y must be greater than or equal to negative 2. Well, that's still what I see. If you look at the graph of red, which I said is partially wrong, it still has a range of y is greater than or equal to negative 2. However, if I look at the range of h of x, which is y must be greater than or equal to 0, that means the domain of its inverse must be x is greater than or equal to 0. And that's what's wrong with my graph. My graph should only be the right half of the parabola. It should only be the part of the parabola where x is greater than or equal to 0. So I need to erase this. And I'll keep those little dots there. Actually, no, I won't. I'm going to get rid of them too. And so that said, now this looks like a reflection. And now I know this must be correct, which means my equation, when I say the inverse of h is x squared minus 2, if I just leave it like that, it's incorrect. In this very similar way to what we looked at in our first question. If I left my equation for the inverse of f of g, if I left my equation for the composite function of f of g of x is just x minus 1, that was incorrect. So going back here, if I go to my inverse, I really need to just adjust and add on, make an amendment to this inverse of h equals x squared minus 2, where I must say where x must be greater than or equal to 0. And now this is fully correct. And now if I also look back into Desmos here, I'll turn this one off and turn this on, and I have the same thing. And please remember as well, there's lots of relationships between functions and their inverses. Some of them are nice and simple, like the x and y values on a graph are swapped around. So if one function goes through negative 2 comma 0, on another function it must go through 0 comma negative 2, and so on. So inverses, again, it's quite interesting. There's a lot to think about them. They can be deceivingly tricky, but at their essence, there's also a lot of simplicity. You're just swapping around your inputs and outputs. And that's where I'm done.